Hello everyone, this is part 3 of J.J. Thompson's charge to mass experiment, and last time we finished solving the system of equations, coming up with our path of a cycloid here by letting all the constants be equal to 1. Now, as I explained, this is your exam question where you're going to do the same thing, but you're going to solve explicitly in terms of m, the mass, h, the magnetic field intensity, uppercase E or E, the electrical field, and lowercase e or E, the charge on the electron. So if you look at your, I'm going to post the exam shortly, and if it's not already there by the time you reach this video, this is the first question on the exam with 25 points. And I want you to do this in terms of the constants. So M, H, E, and E are all constants. So we're going to start the same way. I'm going to get you going on this, and I'll solve at least the first equation for you, and then you'll be just follow the steps that I outlined in the part 2 lecture, and I know it'll be a little bit tedious, but hopefully you'll be successful with this. We're going to start the same way by letting these are going to be our 2 main equations to begin with. Okay, and these are what we're setting out to prove. But we're going to start by, instead of using the differential notation, using the prime notation. So I'll label the first equation, number 1, as Roman numeral 1, and it'll be m x double prime plus uppercase C h lowercase e y prime equaling uppercase E lowercase e. And then the second equation is going to be m y double prime minus h e x prime equaling 0. And note the initial conditions here are stated right here. Here's the initial conditions. And for simplicity, just say x is y, is x prime, is y prime, and they're all 0. Okay, so the same idea as what I outlined when I let everything equal 1. To begin with, we're going to take equation 1, and we're going to solve for y prime, and then we're going to substitute into the equation 2. After we find y prime, we'll find y double prime first, then we'll substitute into equation 2, and then this equation will be in terms of just the x variable and its derivatives. So if we start with the mx double prime plus he y prime equaling uppercase E lowercase e, if I want to solve for y prime, I'm first going to move the mx double prime to the right side. So he y prime equals, I'll say uppercase E lowercase e minus m x double prime. And then we're solving for y prime, so we're going to divide by uppercase E, or by h, uppercase h, excuse me, and lowercase e. So we'll just divide each term by that. So therefore that gives us that y prime is, these lowercase e's cancel, we get e over h, and then minus, since m, h, and lowercase e are constants, put them out in front, of x double prime. And now calculate y double prime, because we're going to substitute into this equation. And so the derivative of e over h, since they're both constants, that derivative is 0. This is just a coefficient, a constant multiple, that's going to tag along in the differentiation process. So minus m over he, and then times the derivative of x double prime is x triple prime. Okay, so now we're going to take that and we're going to substitute into equation 2. So therefore this becomes m y double prime negative m over he times x triple prime, and then minus he x prime is equal to 0. So let's just write this as minus m squared over he x triple prime minus he x prime is 0. Okay, so the easiest way to solve this is to first make the coefficient of x triple prime equal to 1. So we're going to multiply both sides of the equation by the reciprocal, he over negative m squared. And so the right-hand side is multiplied by that as well. Now, when you do this, be careful. If it's non-homogeneous, make sure you multiply the right-hand side as well, because it will make a difference. In this case, it won't, because you're just going to get 0. Okay, now distributing this, the m squared is the negative, the e's, the h cancel. You just get x triple prime. And then minus, when distributed, this double negative makes a positive. And then if we have he times he, that's h squared e squared over the m squared times x prime is equal to 0. So note that that's the homogeneous differential equation. We can get the characteristic equation. So that's r cubed plus h squared e squared over m squared times r equaling 0. We'll factor out an r with r squared plus h squared e squared over m squared is 0. Set each factor to 0. So r is 0 and r squared plus h squared e squared over m squared is 0. And so then we'll isolate the r squared. It becomes negative h squared e squared over m squared, and square root of both sides, plus or minus. Okay, that negative causes the imaginary unit. Square root of each of the squares, or just he over m times I. Okay, so now for the general solution x, it will be equal to, okay, from the real root of 0, c1 e to the 0t, and then plus, this is complex conjugate pairs, a plus bi have the form of e to the at, so e to the 0t, because a is 0, times c1 cosine bt, b is the he over m times t, and then plus c2 sine of that same he over m times the t variable. And simplify this, so c1 plus, oops, should have called this c2 and this c3. So then plus c2 cosine of he over m times t, and then plus c3 sine of dHe over m times t. Okay, and I think that was what I labeled as equation Arabic numeral 1 in the outline of the solution. So that's as far as I'm going to take it. I'm going to say you finish. But at least that gives you a beginning, a start as to how to solve it. And the neat thing is, look at what we're trying to prove. If we look back up here, it's 1 minus cosine Ag over mt, and Ag over mt with the sines. You can see it's taking shape, right? Okay, so you're going to have to do this for y. Just follow the outline from the previous video. Solving for the constants gets a little bit tedious, but that's the whole point of the exercise. Okay, so we're done with Thompson, and we'll move on to approximations of solutions of differential equations. So we'll see you when you're ready.